Something passed through our solar system last year that formed around a completely different star. We in a completely different part of the galaxy, potentially before our sun even existed. And James Webb did not just photograph it, James Webb chemically fingerprinted it. For the first time in human history, we obtained a direct chemical analysis of material from another planetary system, not by sending a spacecraft across light years of space, but because this object came to us. And what Webb found inside this comet is so far outside the range of anything we have ever seen in our solar system that scientists are now rethinking what they know about how worlds are born. Stay with me to the end, because each discovery builds on the last. And the final one is the one nobody saw coming. And subscribe right now, because when the next interstellar visitor shows up, you will want to already understand what this one told us. Let's start from the beginning. On July 1st, 2025, a telescope in Chile picked up a faint moving dot crossing the sky. The telescope was part of the ATLAS survey network, the Asteroid Terrestrial Impact Last Alert System, a NASA-funded system designed to hunt for objects that might threaten Earth. What it found that day was not a threat. It was something far more rare and far more interesting. The dot was moving on what astronomers call a hyperbolic trajectory, a path so fast, so sharply curved, that it could not have originated from within our solar system. No object born around our sun could be moving that way. This object came from somewhere else entirely. It was officially designated 3IATLAS. The 3I means it is the third interstellar object ever confirmed to enter our solar system. The first was Oumuamua in 2017, elongated, strange, and behavior so weird scientists still argue about it. The second was Borisov in 2019, a proper comet, icy and active, but so faint that detailed study was limited. Then came 3IATLAS. And unlike the first two, this one arrived early enough and bright enough for the entire global scientific community to prepare. Hubble, Webb, ALMA, the Very Large Telescope in Chile, spacecraft orbiting Mars, every major instrument humanity had available was pointed at it. When 3IATLAS was first discovered on July 1st, 2025, it was already traveling at about 137,000 miles per hour. That is not a typo. 137,000 miles per hour. It was inside Jupiter's orbit and heading toward the Sun. NASA's Hubble Space Telescope imaged it in August 2025 and estimated its nucleus, the solid core, to be somewhere between 1/400 feet and 5.6 kilometers across. That made it far larger than Oumuamua and far brighter than Borisov. The Hubble images showed a clear coma, a cloud of gas and dust expanding around the nucleus as solar heat vaporized its surface, and a visible tail already forming. Its closest approach to the Sun, called perihelion, happened on October 30th, 2025. At that point, it was never closer than 1.36 astronomical units from the Sun. That is 1.36 times the distance between Earth and the Sun, so it never came inside Earth's orbit. No danger to Earth at any point, but every instrument that could track it was watching. Here is why 3IATLAS matters more than the previous two interstellar objects. Oumuamua gave us almost nothing to work with chemically. It never produced a detectable coma of gas or dust, and it was gone almost before we had time to study it. Borisov was chemical rich enough to analyze, but far too faint for the kind of deep spectroscopic study that could really reveal its origin story. 3IATLAS was brighter than both of them combined. It reached magnitude 9 at perihelion, bright enough that, under dark skies, it might have been just barely visible to the human eye. And because it was discovered months before perihelion, scientists had time to coordinate. The result is something unprecedented. A comet from another star system, studied by more instruments simultaneously and in more chemical detail than any previous interstellar visitor. And what those instruments found has produced discovery after discovery since the comet began fading away. Let's go through each one and understand that each discovery comes with a number, a measurement, a published paper. These are not opinions or theories. This is data. The first major discovery came from NASA's Swift Observatory. Swift carries an ultraviolet telescope that was pointed at 3IATLAS in July and August 2025, while the comet was still approaching the Sun. Scientists detected the faint ultraviolet glow of hydroxyl gas, which is what water produces when it breaks apart under sunlight. This was the first detection of water from an interstellar object, not just water ice, active outgassing of water vapor, happening at a rate of about 40 kilograms per second. At a distance from the Sun, where most solar system comets have not yet activated their water ice at all, 40 kilograms of water per second, evaporating off a comet from another star system in our own neighborhood. But that was just the opening. The deeper discoveries required deeper instruments. In April 2026, a team of researchers led by PhD student Luis Salazar Manzano at the University of Michigan published a paper in the journal Nature Astronomy. They had used the Atacama Large Millimeter Submillimeter Array, ALMA, to analyze the water coming off 3IATLAS. Not just detecting water, measuring the specific type of water it contained. Water is made of 2 hydrogen atoms and 1 oxygen atom, but hydrogen comes in 2 forms. Regular hydrogen has just 1 proton in its nucleus. Deuterium, sometimes called heavy hydrogen, has 1 proton and 1 neutron. When water forms in extremely cold environments, below about 30 Kelvin, that is minus 406 degrees Fahrenheit, chemical reactions incorporate more deuterium into water molecules than they would at warmer temperatures. The colder the environment where water forms, the higher the ratio of deuterated water to regular water. This ratio, the amount of heavy water compared to regular water, is a frozen record of the temperature of the environment where a comet was born. It does not change as the comet travels through space. It is a chemical fingerprint of its birthplace. The ALMA team measured this ratio in 3IATLAS, and the number they found stopped them cold. In comets from our own solar system, roughly 1 molecule of deuterated water exists for every 10,000 molecules of regular water. That is the baseline we know. The ALMA measurement for 3IATLAS revealed a deuterium to hydrogen ratio more than 30 times higher than typical solar system comets. More than 40 times higher than the ratio found in Earth's oceans. 30 times higher. Not 30% higher, 30 times. Lead author Luis Salazar Manzano said directly, "The amount of deuterium with respect to ordinary hydrogen in water is higher than anything we have seen before in other planetary systems and planetary comets." He said, "We now know that the cloud of gas that formed the star and other planets in the system where 3IATLAS came from was likely very cold and had very different conditions than the environment that created our solar system and local comets. This is not a subtle difference. This is a chemical signature so extreme that it falls completely outside the range of everything we have measured in our own solar system. It points to 3IATLAS forming in conditions far colder, far more extreme, and far more ancient than the environment that built our world." The paper was published in Nature Astronomy in April 2026 and has already been described as one of the most fundamental measurements ever made of material from another planetary system. Because the abundances of deuterium and hydrogen were set during the Big Bang itself, this measurement connects directly to cosmology, to the very conditions that preceded all star formation. Every comet is a chemical capsule. 3IATLAS just opened a capsule from a place and time we have never directly touched before. James Webb observed 3IATLAS multiple times. The key observation for chemical analysis happened in December 2025, roughly 2 months after perihelion, as the comet was heading back outward and away from the sun. Webb used its MIRI instrument, the mid-infrared instrument, and specifically its medium-resolution spectrometer, which breaks infrared light into its component wavelengths at a very fine level of detail. The spectrometer is what is called an integral field unit. It simultaneously captures a spectrum at every point across a small patch of sky, so it does not just measure what gases are present. It maps where they are distributed in the space around the nucleus. The results were published on June 1st, 2026 in the astrophysical journal Letters by lead author Matthew Belyakov from Caltech and co-author Ian Wong from the Space Telescope Science Institute. Webb detected 3 distinct chemical species in the gas cloud surrounding 3IATLAS's nucleus: water vapor, carbon dioxide, and methane. That third one is the one that matters most. This was the first direct detection of methane on any interstellar object in history. Not inferred, not calculated indirectly, directly detected. The infrared fingerprint of methane, clearly resolved in Webb's spectrum, unambiguous. Now, why does methane matter so much? Because methane is extremely volatile. It sublimates, turns from ice directly to gas at very low temperatures. In our solar system, methane ice on comets only releases its gas when a comet is very close to the sun, or not at all if the methane was buried deep beneath the surface. The fact that Webb detected methane in 3IATLAS and that this methane appeared after perihelion rather than before tells scientists something specific. The methane was not on the surface of the comet when it entered the solar system. It was buried, hidden underneath layers of other ices. Only when the sun's heat penetrated those outer layers deeply enough, during and after perihelion, did the methane begin escaping. That has an implication. It means the surface of 3IATLAS that we were looking at before perihelion was a processed crust, altered by radiation exposure during billions of years of travel through interstellar space. Beneath that crust was pristine material, untouched by our sun, locked in place since the comet formed. And the methane coming out after perihelion is a signal from that untouched interior. Webb's MIRI images also revealed how the 3 gases were spatially distributed around the nucleus. Water vapor spread far from the nucleus in all directions, extending across the entire coma, because much of it was being released not just from the nucleus itself, but from icy grains suspended throughout the gas cloud. Carbon dioxide and methane, in contrast, were tightly concentrated close to the nucleus. That spatial pattern is direct visual evidence that carbon dioxide and methane were being released from solid ice on the nucleus, not from diffuse grains in the surrounding cloud. And the amount of methane relative to water was significantly higher than what is seen in comets from our own solar system. Scientists describe the methane to water ratio as a flag for formation in a colder, more distant environment around a foreign star. The carbon dioxide levels were also exceptionally high, again outside the range typical for solar system comets. NASA's own statement on this discovery was unambiguous. They said both of these findings, the methane and the elevated carbon dioxide, point to a very different formation environment and chemistry than the vast majority of comets that formed within our solar system. Webb also tracked how the gas production from 3I/ATLAS changed as it moved away from the sun. Water production showed the most dramatic drop as the comet receded. This makes physical sense because water, while volatile, requires more heat to vaporize than methane or carbon dioxide. As 3I/ATLAS got farther from the sun and cooler, water shut off first. Carbon dioxide and methane persisted slightly longer. The way the different gases switched off in sequence matched predictions for an object with that composition, further confirming the measurement. The European Southern Observatory's Very Large Telescope in Chile had been observing 3I/ATLAS throughout late 2025 and into early 2026. Specifically, a team led by astronomer Cyrielle Opitom at the University of Edinburgh used an instrument called UVES to measure something called isotopic ratios. These are the relative amounts of different forms, different isotopes, of the same element. The team focused on carbon and nitrogen isotopes and cyanide molecules present in 3I/ATLAS's gas cloud. Carbon comes in two isotopes, carbon-12, which is the common form, and carbon-13, which is heavier. Nitrogen comes in nitrogen-14 and nitrogen-15. The ratio of the light isotope to the heavy isotope is sensitive to the physical conditions, the temperature, the radiation environment, the chemical history of the place where a comet formed. And critically, these ratios are not expected to change much as the comet travels through space. They are set at birth. The VLT measured these ratios in 3I/ATLAS. For carbon, they found a ratio of approximately 147. For nitrogen, approximately 343. Now here is the context that makes those numbers striking. In solar system comets, the carbon-12 to carbon-13 ratio is typically around 90. The nitrogen ratio in solar system comets typically falls between 130 and 170. The VLT numbers for 3I/ATLAS fall entirely outside the range of any solar system comet ever measured. Not at the edge of the range, outside it completely. These values, published in Nature Astronomy on July 6, 2026, are consistent with 3I/ATLAS forming in what scientists call a metal-poor, cold environment, in an earlier stage of the Milky Way's history, when the galaxy had not yet accumulated as many heavy elements through generations of star formation. They are consistent with formation in the outer disk of a star that was older, colder, and chemically less enriched than our Sun, a star that may have formed billions of years before our solar system. Rosemary Dorsey, an astronomer at the University of Helsinki and part of the collaboration studying these findings, said it directly. 3I/ATLAS is a really exciting opportunity to probe the composition of another planetary system, one that formed long before our Sun and the solar system even existed. Long before our Sun and the solar system even existed. When you put all of this together, the extreme deuterium ratio in the water, the methane buried beneath a radiation-processed crust, the carbon and nitrogen isotopic fingerprints pointing to an older and colder home system, a portrait emerges. 3I/ATLAS was born in the outer regions of a protoplanetary disk surrounding a star that is likely older than our Sun, potentially much older. The star itself may have formed in a colder, less chemically enriched region of the Milky Way in an earlier era of the galaxy's history. The comet formed in conditions far colder than the environment that built our solar system's comets. At some point, through gravitational interactions in its home system, perhaps during the migration of planets or during a close encounter with another body, 3I/ATLAS was ejected outward. It entered interstellar space, and it has been traveling ever since. For how long? Possibly billions of years? Long enough to develop a radiation-processed crust? Long enough for the galaxy to age around it? And then, in 2025, completely by chance, it passed through our solar neighborhood, close enough to the Sun for its ices to activate, close enough to Earth for our telescopes to capture its chemical signature. James Webb got to it in December 2025, while it was still producing measurable gas, still close enough to sun heat. Webb stretched, pointed in a direction it was not originally designed to track, fast-moving solar system objects, and captured the first mid-infrared chemical fingerprint of an interstellar object ever obtained. Webb scientist Martin Cordner at NASA Goddard had been preparing for exactly this moment since Oumuamua arrived in 2017. After Webb launched, He and colleagues asked the Webb team to have a plan ready for any newly discovered interstellar comets. When 3IATLAS was found in July 2025, that plan activated, and the result is now published, reviewed, and confirmed. The December MIRI data forms what researchers described as the most chemically detailed record of material from another stellar system ever assembled, obtained not by sending a spacecraft across light years, but by pointing an existing telescope at a visitor that came to us. Think about that. We did not need to travel to another star system to sample material from one. The material came to us, and the chemistry inside it is so different from everything we know in our solar system that it is reshaping what scientists thought they understood about how planetary systems form across the galaxy. Our solar system's comets have a certain range of deuterium ratios, a certain range of carbon and nitrogen isotopes, a certain set of molecules, and in certain proportions. Scientists have studied hundreds of them and assumed that range was broadly representative of comet chemistry in general. 3IATLAS has blown that assumption open. One comet from one other system, and already the numbers fall completely outside everything measured here. Researcher Cyrielle Opitom, who led the VLT isotopic study, concluded with a statement that captures where the field now stands. She said the field of interstellar objects is still very new, and we do not really know what to expect. Every time a new one is discovered, we have new surprises. That is the honest position. We do not know what to expect, because 3IATLAS is only the third one. 3 interstellar objects in recorded human history. And already the second and third have told us that solar system chemistry is not the universal standard we assumed it was. Now here's the thing that should stay with you. 3IATLAS is gone. It passed its closest point to the Sun on October 30th, 2025. By early 2026, it was already past Jupiter's orbit heading outward. The Very Large Telescope was already struggling to track it by the time the July 2026 paper was published. It will not return, ever. Once it exits our solar system, it disappears into interstellar space for billions of years if it is ever detected again by any civilization anywhere at all. Everything we know about it, every chemical measurement, every spectral fingerprint, every spatial map of its gas distribution, had to be obtained in a narrow window of months. The scientific community mobilized every major telescope it had. Webb, Hubble, ALMA, the VLT, Spherex, TESS, SWIFT, the Europa Clipper spacecraft, orbiters at Mars from ESA in China. Every available instrument was directed at it. And that campaign produced more first-ever measurements of an interstellar object than everything in human history before July 2025 combined. The methane detection is a first. The deuterium water ratio measurement is a first. The carbon and nitrogen isotopic fingerprint of an interstellar comet is a first. The mid-infrared chemical spectrum of an interstellar object is a first. Every single one of these firsts came from a visitor that passed through our neighborhood and left a window of a few months to be studied. And the numbers it left behind: 30 times the deuterium ratio of our solar system, isotopic fingerprints outside the range of every solar system comet, methane buried beneath a radiation crust billions of years old. Those numbers tell us that the solar system we live in, the comets we have cataloged, the chemistry we have measured, may be one kind of place, in one kind of galaxy era. And out there, in other parts of the galaxy, in older systems, around colder stars, under conditions we cannot yet fully model, worlds are forming with chemistry that looks nothing like ours. The Vera Rubin Observatory, which officially began its 10-year legacy survey of space and time on June 30th, 2026, is expected to find substantially more interstellar objects than any previous survey. Scientists estimate it could detect 6 to 50 interstellar visitors over the course of its 10-year mission. Each one is a new capsule of chemistry from a planetary system we cannot otherwise reach. Each one is a first look at how worlds formed around a different star. We are at the very beginning of interstellar comet science. We have 3 data points, and already the third one has told us the range of planetary chemistry across the galaxy is far wider than we suspected. If you made it this far, you now understand something that most people on Earth have never heard, explained without any exaggeration, exactly as the science shows it. Every paper cited in this video is real. Every number is measured. Every quote is from the scientists who made the discovery. Subscribe, because the next interstellar object is coming. Rubin will find it. And when it does, and when Webb and all the telescopes turn toward it, this channel will be the place to understand what it means before anyone else has processed it. Do not miss that.